After finding food, our next major problem is building a shelter. But what does this primeval need got to do with this? One of the biggest brick structures in Europe.
Years ago, in Stockport, the Industrial Revolution was at full steam ahead, and that meant new buildings. In one generation, Stockport exploded with factories, mills and workers' housing. And Stockport wasn't alone, it was like a construction big bang going off around the country. New materials and new ways of working. 10,000 years ago, somebody grabbed a bit of riverbank, made it into a shape and dried it in the sun and called it a brick. They've been around for that long. They literally surround us. They're incredibly familiar to us. But it's easy to forget that they're not found, they're made, they're manufactured.
But mass production was going to need new technology.
It all starts with this stuff, clay. At first sight, it just looks like extra specially sticky mud, but when you look at this face here, you can see the stratifications of the soil. Lighter, browner areas at the top, leading into these darker areas here, these greyer areas. And they mix these, and that's part of the brickmaker's art, in order to get the best consistency for brickmaking.
Mixing the clay was the first process to be mechanised.
This is a pug mill. Its job is to extrude the clay to remove air from it and also to mix it further. And you get this lovely stuff. This work used to be done by itinerant families of brickmakers. The kids would trample the clay to remove all the stones, and then the parents would make the bricks. Now, the length of a brick is twice its width, which is half its height, 421. Sand that, get my clay, and add that to the mould. Smooth it off, reserving the excess for the next brick. Then, that goes on there, onto the barrow, ready for drying, and you start the entire process again. A good brickmaker can make 900 bricks a day. I obviously am not a good brickmaker.
The wet bricks are left to dry out under these shelters known as hacks.
The next stage, after they've dried, is the kiln.
The earliest kilns were updraft kilns where the heat rises up through the bricks. But the problem was you just didn't get a consistent result.
And then in the early 19th century, the brickmakers came up with this, the downdraft kiln. That chimney there has got nothing to do with the heat needed to actually fire the bricks. It's a huge flue. It creates a massive updraft, which pulls the gases from the fires in a ring round the kiln, up and down through the bricks. Once inside, you can really see how it works. Hello. These are the hearths that ring the kiln. Here's the kiln, here. The bricks are inside there. And here is the base of the chimney that provides the flue. The flue under here goes underneath, pulling the heat and gases from the hearths round the kiln, up, down through the bricks.
This kiln works on a 2-week cycle. Takes 4 men 2 days to stack it with up to 12,000 bricks. Then 2 days to fire it up to its working temperature. This is called tanning. It burns for 36 hours, reaching 1150 degrees, and takes 2 more days to cool down. Finally, the bricks can be unloaded.
There's a good story about this kiln. The 2-day tanning period used to be controlled by a bloke called Tom. And one day, Peter, who runs this brickyard, said to Tom, Why do we take 2 days to tan the kiln? He says, I don't know. We always have done. And I've always wondered why.
So tradition still plays a big part in the making of these specialist bricks. But it's essentially a niche market.
These kilns make beautiful bricks. Very labour intensive and they take their time. But with the arrival of the railways in the 19th century, kilns like this just weren't good enough. It wanted quantity, not quality. In the 1840s, the railway builders across Britain used 2,000 million bricks. In 1842, when this viaduct was opened in Stockport, it was the largest brick-built structure in Europe. Its bricks could stretch from John O'Groats to Land's End and back again, although why ever did you want to do that, I don't know. At the height of its construction, there were 600 men working day and night to complete it. The railway's insatiable demand for bricks meant that production had to shift up a gear. The breakthrough came in 1858, when a German railway engineer, Friedrich Hoffmann, invented a kiln that could be fired 24 hours a day, 7 days a week.
The Hoffmann kiln used a network of flues to circulate hot air on a continuous cycle around multiple chambers. This one in Scotland had 24 chambers, each of which could hold 14,000 bricks.
The kiln would be fired from up here. One chamber would reach 1100 degrees centigrade to fire the bricks. You then cool it down and move on to the next chamber. This one's cooling, this one is reaching firing temperature. It's continuous mass production. Relentless, one chamber at a time, cooling, curing, firing, cooling, curing, firing, all the way around. These Hoffmann kilns were only economical if you were making at least 2 million bricks a year. Some of them ran continuously for 50 years. Hot and thirsty work. Cheap mass-produced bricks were used in their millions for workers' houses in Stockport. And for roofs, they could now get the best material available. Slate from Wales.
This slate quarry at Dinorwick opened in 1787 and had over 3,000 men on the payroll by the 1870s.
They cut the stone on terraces, working 2,000 feet above sea level. It was hard, dangerous work. They used black powder, gunpowder, to blast the rock from the face. But it was worth it. Look at it. Slate was big business.
Blasting tons of rock off a face with black powder didn't make for a safe working environment. You never knew what could happen up here. And to protect themselves from rock falls, all they wore were bowler hats.
In the 150 years this quarry was worked, 360 men died up here, often 2 and 3 at a time, buried under rock falls. These quarries were run on a bargain system. The bargain was a piece of rock about 20 foot square. The quarry steward would haggle with the team about what the value of that rock was and the slates it contained. So their wages depended on driving a hard bargain.
The giant slabs then had to be cut down to size. Nowadays it's all mechanised, using modern power tools. The great thing about slate is that it's made up of layers of compressed sediment, and if you are skilled enough, you can split these layers to form roofing slates. The final splitting is still done the traditional way, using a hammer and chisel. And it's a really skilled job. It takes years of practice to get up to the speed the quarrymen work at. At least now they work indoors. In the 19th century, it was a very different story.
All that was done on the hill in these open shelters called gwalia, made of recycled slate and tree trunks. They're goat buyers now, but you can still see the marks of the men who worked here. That was where they kept their tools, and that's where they hung their coats.
Once you'd cut the slates to size, you wanted to get them off the mountain quick. This business is about bulk and distribution. You don't want them here, you want them on roofs. So they're packed in these trucks rather beautifully here, and then this drum and this cable will lower them down the mountain. This is an inclined plane. Works on the basic principle that the heavier loaded trucks will pull up the empty trucks. Then they are loaded onto the company's fleet of steamers, and from thence, the Empire. It's a wonderfully simple, effective piece of Victorian engineering. The slate quarries were the largest employers for miles around. Working on the remote hillsides, quarrymen had to learn to do everything themselves. It was a training for life.
A machine shop apprentice would have been taught to use a lathe for turning loco wheels, drilling machine, slotting machines to repair everything from steam engines to chisels, all driven by shaft drive and belt. And power was provided by this enormous water wheel. It's the biggest water wheel on the mainland of Great Britain. It's got 140 buckets, and if water fills only one of them, it's enough to set the wheel in motion. And then, of course, its weight will do a lot of the work, and it provides, at full chat, 80 horsepower. It's a marvellous bit of machinery. They even had their own foundry and a casting floor big enough to cast anything they needed. Rails, wheels, cogs, windows. Here's the pattern for a window, still available for use. And that is the iron window it made. And they were bang on the money, because in the 19th century, iron was the new material for building. There's been a market here at Stockport for 800 years. The Industrial Revolution didn't change that. What it did was provide new materials for the building of their covered market in 1861. It's their mini Crystal Palace built of iron and glass, 10 years after Joseph Paxton's design for the Great Exhibition in 1851. They called it the umbrella on stilts because originally the sides were uncovered. Surrounded by heavy brick and tile buildings, it must have been amazing. It's so bright and light and airy. The glazed roof is supported on cast iron columns, very slender. They're very good in compression, and tied together with wrought iron bars. That's very good in tension. We're used to light, airy buildings made of glass and steel, but the Victorians weren't. Imagine walking out of your brick and tile built terrace into this light, open space. The nearest equivalent must have been walking out of your wattle and daub thatch cottage into a medieval cathedral. And like the medieval cathedral builders, the architects who made this were working at the edge of their understanding of the materials. It was really trial and error. But trial and error is a very dangerous game for builders and engineers to be playing. To use new materials in untried and tested ways, you need some kind of quality testing. And a Scottish engineer, David Kirkcaldy, made testing his business. He lived by one creed, and one creed alone: facts, not opinions. Using this huge hydraulic ram, David Kirkcaldy offered to test things under various strains: pulling, thrusting, bending, twisting, shearing, punching and bulging. And we are now going to break something.
His machine pushed the new materials to their limits.
It's 47 feet long. It weighs 116 tonnes. It uses water pressure at 4,500 pounds per square inch to exert a pull of 300 tons. What Kirkcaldy was doing was using the massive power of this machine to evaluate and tabulate materials tested to destruction. The great machine's first job was to test the wrought and cast iron to be used in the construction of a new bridge over the Thames at Blackfriars in 1866. Seems to have stood the test of time, but Kirkcaldy's were also brought in when things went disastrously wrong. When the Tay Bridge collapsed in 1879, killing 90 people, parts of the failed structure were dredged from the riverbed, cased, sealed and brought here for testing.
The results suggested the iron girders were not up to the job.
David Kirkcaldy's scrupulous attention to detail and outspoken honesty had made him many enemies. Parts of his report were suppressed and worse, some of his calculations were distorted. Facts, not opinions, was not everybody's idea about how to conduct business.
At least when the engineers came to build the Great Forth Railway Bridge, they took account of Kirkcaldy's recommendations and used mild steel, the most advanced material available.
But of course, traditional materials always had a part to play in building. When the burghers of Stockport wanted to show off with their new town hall, they built the front bit in lovely limestone. Very nice, tell your mother. You can see why it was called the wedding cake. Building in stone gave you importance, durability and prestige. But in the 19th century, to capitalise on that at lower cost, builders started to develop artificial stone. That's limestone they're digging here in this quarry in Derbyshire, one of the oldest building materials known to man, and it's been the main ingredient in cement for thousands of years. But in 1824, a builder, Mr. Joseph Aspdin, patented a new type of cement. He still used limestone as a basis, but it had to be ground very finely. But Mr. Aspdin had a cheap solution for that. I take a quantity of limestone, such as used in the making or mending of roads, then I take it from the roads, after it's been reduced to a fine puddle. Aspdin's secret was that he combined his powdered, puddled limestone with clay and water, let the mixture dry, and then heated it to a very high temperature, 1400 degrees centigrade. The resultant clinker he then ground, and that gave him this Portland cement. And that could be used to coat the outside of buildings and make them look like they were made of Portland stone, a very desirable, high quality building material that Aspdin was keen to emulate. And that's why he called it Portland cement. But you can't make a building out of cement. To use Portland cement as a building material, you have to mix it with other ingredients to make concrete. You need sand and aggregate in the time-honoured proportions of 3:2:1. So 1 cement, 3 aggregate, and 2 sand. Aspdin's Portland cement was an excellent material. It cures quicker, it goes off quicker than previous cements. It's more waterproof, it's stronger. It was a real breakthrough, and like all breakthroughs, it took a while to catch on.
Another opportunity for Kirkcaldy's testing workshop.
Once again, came down to trust. Was the material fit for its purpose? Was it safe? This is his cement tester. It's a very simple but elegant device. This tower contains lead shot, fed through this chute into this weight, this counterweight here, acting on the material to be tested. There's the sample clamped between those two jaws. When it finally goes, that comes down, this drops down, hits this lever, shuts off the supply of shot. You can then take the bucket off, weigh it, and it will give you the exact breaking strain. Excellent. A simple laboratory device, but it aided the development of what was to become the building industry's most used material. What concrete needed was a kickstart in the residential market. It had a lot of competition with traditional materials, beautiful houses here in Bridgewater. But in 1851, that's what it got. It got a show house built by a Mr. John Board. He designed this. Unfortunately, at the moment, it's a little bit the worse for wear.
The house is little more than a roofless shell, held up by scaffolding and too dangerous to enter.
But you can see what Mr. Board was trying to do. This is the ultimate showcase for Portland cement. Anything that was ever made in stone, he has attempted to replicate in concrete. And I mean anything. An armorial crest above the door, a rusticated stone course, corbelling with some fretted decoration, then a deeply incised imitation masonry course here, mullioned windows, niches for statuary, and blow me, an arrow slit. The only thing he hasn't got is a portcullis. But as a keen scholar of vernacular building styles, here, behind this door, is the pièce de résistance. Spiral staircase. It's exactly like a medieval spiral staircase. It's constructed segmentally of concrete, which is exactly how we do it today.
A heritage charity is campaigning to rescue the house and restore it to its former glory. They need about £1 million, and at the moment, they're a long way off.
We spend millions on the upkeep of medieval wooden buildings, and so we should. But one of the first buildings to utilise Portland cement, which is indispensable to modern buildings, we leave to rot. I'm grateful, aren't we?
Today's builders, architects and engineers take for granted working in concrete or in brick or constructing fantastic creations in glass and steel. But they owe so much to the pioneers of the 19th century. The buildings of Stockport, like the buildings of so many industrial boomtowns, tell the story of a revolution that transformed people's lives. The coming of the railways, the building of huge mills, factories, the massive increase in population. In order to deal with all that, the building industry was transformed from a local craft to a national industry.